go over it.
On homework 2?
Yes.
Okay. Is that the greatest common divisor of
2n plus 1 and 4n squared plus 1.
2n plus 1 and
4n squared plus 1. You got that. All that equals 1. Yeah.
right. So I think everybody tried through this using the Euclidean algorithm, which is good. And I gave you, I mean, that was kind of the hint that I gave you, right? So the hint was actually the first step in the Euclidean algorithm. So it was, I think it was 2n squared plus 1, I'm sorry, 4n squared plus 1 equals 2n minus 1 times 2n plus 1 plus 2. So if you look at this, this is if you divide 4n squared plus 1 by 2n plus 1, this is what you would get using the division algorithm. And you can, some of you verified that with long division. So this would be the quotient, and this is some quotient times the divisor plus the remainder. Okay, so then the Euclidean algorithm says then you can repeat this with 2n plus 1 and the previous remainder, which was 2. Okay, well if I divide 2n plus 1 by 2, then 2 will go into this n times, so this is n times 2, and the remainder is 1. Right, so if you divide this by 2, this is a factor of 2, and then the remainder is going to be 1. So then, by one more step, I use this, and I divide 2 by 1. Well, 1 goes into it 2 times with a remainder of 0. So the last non-zero remainder is the greatest common divisor. You could show this kind of like directly with a proof. You could also, so is there any questions about that though? So you could do another proof without the Euclidean algorithm and show that, you would show that the greatest common divisor of these two is either 1 or 2, but this is odd, so 2 can't divide this. So you could try that if you want to. But this is sufficient for that. Okay, any other questions on homework 2? Okay. So if you didn't get my comments somehow, or there's a discrepancy, I can submit that again later today. We might even take a little break here after, because we've got like a 2-hour class here, so I'll probably take a little break and I can resubmit that stuff to you guys. All right, so that's all I want to say on homework 1 and homework 2. So next, any questions about homework 3, which is due tomorrow, right, midnight?
Whenever we're using the sieve of their cost views,
Right.
do we need any verbiage there?
No, it's just kind of, you would just write out the numbers 1 through 120 and
Yeah. But
make a video, send it to me as your, no.
we don't need to write anything.
No, just follow the process and you'll see, just show that work and then just say, these are the primes, less than 120. Yeah, that's the way it works.
Just the circle.
Yeah, just circle the prime. That's kind of what I did on
Yeah, as
the
long as they're
example.
circled, that'd be fine. We don't have to do. If you want us to list them.
Yeah, at the end, just make a little conclusion. Like, so the primes less than 120 are blah blah blah. Just list them off. So, number 7. Okay, so I don't have the homework in front of me. You have? Thank you. Yeah. So, has any of you had experience with congruences before this point? Some of you have. Some of you haven't. So when I've taught number theory before, and there's a saying in mathematics that I think it's a famous mathematician says that in math you never learn anything, you just get used to it. And so congruences are kind of that way. You just once more you deal with them, the more used to them you get, and they don't seem that weird. But so these congruences. Was everybody okay on number 6?
Yeah.
So you guys, So so let me see. So for example, well, I don't know how to work these out, right? But, I mean, the idea is, so this was number 6. Hey, I know you asked for 7, but just to kind of talk about kind of how do you solve these. So did you guys figure out that you can always add multiples of 7 or subtract multiples of 7, right? So I mean, so really, I think of these as congruences as things have the same remainder when divided by 7. So 8 would have the remainder of 1 when divided by 7, and so on. So the question for number 7 though says, do there exist integers x such that 12x is congruent to 9 mod 6? Right? So did you just try to solve it? Is that how you?
Well, the first thing I did is that from your video it says that if 12 and 6 have a GCD, then you can divide all 3 of them.
Right.
Okay, so I divided all 3 of them by 3.
Right. Right.
And came up with 4x is equivalent to 3 mod 2.
Right. Okay.
And then here was my question, because because 4 and 2 still have a GCD.
Right.
I can actually subtract from the 4 side until I get something that would work.
Okay.
But if you actually look at that, that says that 2 divides 4x minus 3. And 4x minus 3 is always
Yeah.
odd.
Yeah, so that's good. So you convert it back to the definition. Does 2 divide 4x minus 3?
No.
Is that possible?
From there, I took it to 4x minus 3 equals 2k,
Okay.
and then proved it from there.
And then you prove that it what?
Does not.
That it does not have a solution. Yeah. So there's many ways to show that this doesn't have a solution. So that's kind of, you need to, when you guys write this up by tomorrow, you can do this many different ways, but yeah. So this one doesn't have a solution.
You could even take the 4.
And that's basically how you show it. Is you just try to solve it, and you show that you can't solve it, right? And then justify why you can't solve it. I mean, just look at this, right? I mean, this is 0 mod 2. This is 1 mod 2. I mean, because this is, in other words, this is an even number. This is an odd number. So an even number, it can't be congruent to an odd number mod 2. But essentially what it comes down to, the logic is an odd number can't equal an even number. So 2 cannot divide an odd number. And so another thing I want to point out, a common mistake, say you had a congruence like this, 4x is congruent to 3 mod 2. I see people, try to divide by 4, and they'll get, so 4x divided by 4 congruent to 3/4, mod. I mean, so you can't divide if you don't end up with integers, right? So that's why.
Can we take a run at this?
Sure. Oh well. Actually, no. I decided to just use my webcam here and film myself at the board.
Okay.
Yeah, but in fact, I should have worked out these kinks later.
We'll work.
How about after class? You think I can come by and?
We'll come back in.
Okay, great. So you can't divide if you don't end up with integers. That's why it's one of these common tricks with congruences. You kind of keep adding multiples of the modulus until this number is divisible by this number. That's another trick you can use. And then you got to worry about that cancellation rule, right? That if you're divided by a number that's relatively prime to the modulus, you have no problems. But if like here we divided by 3, you got to reduce the modulus by that common divisor as well. Okay. Questions? Yeah.
Right there, you said that you try to divide by 4,
Right.
and it doesn't give you the integer.
Right.
Does that not also prove that you're?
Can you divide by 9 here?
No.
No, but this one's solvable.
Gotcha.
So it's you just got to get this, you got to keep adding multiples of 7 here, for example. One way to solve this would be keep adding multiples of 7 until this number is divisible by 9, and you can divide by 9 at that point. Okay. And some of these, so I also had a question about so I know you guys recognize I posted a book, textbook. So are you guys using that textbook at all? Because there are examples of like congruences and things like that in that textbook. I mean, one reason I posted that is because it's free, and so. But there are examples too in there. So and just in future, if you have a question, that might be one resource. I mean, if you can find other resources, I know there's tons of stuff on the internet. But see examples of congruences solved and so on. What I've noticed in a textbook, they'll often do stuff like, oh, just by inspection, I see that the solution is blank. So basically, they don't. It's just kind of a trick of mathematicians, right? You don't show any of the details. You say, oh, the answer is this because it works, right? And so that doesn't. That's not really what I'm looking for on homework, right? Like I say, okay, well, the solution is x equals 2 or whatever, because. Just because it is, that's the solution. I do want you to show some steps. Yeah, James?
Could you do a different congruence that's not on the homework?
I did in the videos, didn't I? No. Did you? I don't have anything planned. Well, I could. Let me get. I want to make sure I have one that's solvable. You can see. You can make up a congruence that's not solvable. I actually have a hard copy of that. Yeah, I got this is the text. Oh, she did get these those? Okay. Yeah, so that textbook is much more advanced than this one is, right? But this is really at undergraduate level. So there's some more difficult, any kind of like theorem that we proved is often like a more complicated, more general theorem proved in this text. I don't think there's that many congruence problems in this text because it's at the graduate level. But let's see. So you'll see next week. So I kind of ran out of time yesterday for posting the videos. I usually try to post the videos on Mondays. So probably by tonight I'll post videos and I'll actually show you how you can show that. How you can tell if a linear congruence like this is solvable. And I will completely determine the solutions to these linear congruences. So right now I just wanted you to kind of play around with maybe the definition of congruences and also just using these techniques of adding multiples of 7 or subtracting multiples of 7 and solving congruences like that. But I'll show you, this, so stay tuned for solving linear congruences completely. Let me give you an example of. So I don't want to use the technique that I did in my videos yet to solve these. Because I want you to use the definition of congruences. Let's see here. So. I can't remember. I may have solved this one in the video. So 5x. Did I? So I don't need to do that one again. I think that's one of them. There's. How about?
Dr. Desarge.
Yes. Yes. Yeah, those are Chinese remainder theorem thing. So you have to solve all 3 congruences at the same time. So it's a little slightly more complicated. So let's look at this one. How about 10x is congruent to 8 mod 6? So
Add 6 to the 8.
you could do that, yeah. Keep adding 6 to 8, or to what you're saying?
Yeah.
Okay. And you notice there's also common factor of 2 you divide, I guess. You make things smaller, but then you'd end up changing the modulus. So it might be, so can you keep adding multiples of 6 until you end up with a multiple of 10?
Now, if you divide them all by 2, wouldn't you end up inevitably still changing that, still adding that new, which would end up being 4 instead of 8? Wouldn't you still add multiples of 3 to make it a multiple of 5? You know what I mean?
Right, yeah, you solve it that
That
way.
way you're doing it the
Yeah.
same-
So this one isn't too bad because you just add 6 twice and you already. So 10x is congruent to 20 mod 6. So now I can divide by 10. But what is the common divisor of 10 and 6? Greatest common divisor of 10 and 6? 2. So I'd have to divide the modulus by 2. So I get x is congruent to 2 mod 3.
Which I guess if you reduced it to mod 3 first, you would get that answer.
You get that answer.
So if you're basically
Yeah.
reducing a step, or you're adding a step at first.
Yeah,
but
they're
reducing a
they're
step-
equivalent. Yeah, I mean they're equivalent
Yeah, you're
ways to
reducing
solve
it.
it. So you get, so if we solved it by dividing at first by 2, divide everything by 2, you get 5x is congruent to 4 mod 3, and then adding 2 multiples of 3. I mean it's essentially, you get 5x is congruent to, if I had 6, I get 5x is congruent to 10 mod 3. So x
And then
is
yours
congruent
would
to
use- would just
2
use just 1.
mod 3.
So, in the first step, you divide everything by 2. In the last step, you only divide 2 of them by 5. So,
Right.
when do you divide them all, and when do you only divide?
When do you divide the modulus? When do you reduce the modulus?
Yeah.
It's if you divide by a number that's not relatively prime to the modulus, you do have to divide by the greatest common divisor
Okay.
of your whatever quotient, I guess. So divisor, I mean. So here I divided by 2, and 2 is not relatively prime to 6, so I've got to divide 6 by 2. But here, when I divide by 10, I don't divide by 10, I just divide by the greatest common divisor
Okay.
of 10 and 6. So that was,
Got it.
there was the theorem on division. So if you have, if you have ax congruent to b mod m, right? If you want to divide by a, then if d is the greatest common divisor of a and m, then when you divide by a, so x is congruent to b over a, assuming that's an integer, mod m over d. You divide by the, when you do the cancellation, you divide by the greatest common divisor of a and m. Okay, so that's why it's nice that in this step, 5 is relatively prime to 3. And it's still true, but you're really dividing by 1 here. But that's why it looks like you're not changing the modulus when you divide by 5 here. Okay. So x is congruent to 2 mod 3. It's a solution. So technically, the original congruence was congruent to mod 6. You could just leave it like this, like you leave your answer like this. But if x is 2 more than a multiple of 3, it's also 2 more than a multiple of 6. So if x is congruent to 2 mod 3, x is also congruent to 2 mod 6. So if you wanted to write an answer, in terms of the original modulus, x is also congruent to 2 mod 6.
After you divide by 2, is there a reason why we can't subtract 3x?
No.
Okay.
So if you subtract 3x, you'd have, what, 2x congruent to 4 mod 3?
Yeah.
You could
Yeah,
do 2x
that's fine.
plus 1.
Yeah, and then divide by 2. So,
Okay.
yeah. So there's many ways to solve it, right? You guys all remember the proof that's over 2,000 years old that there are an infinite number of prime numbers? So So this is called Euclid's theorem. It's named after Euclid because Euclid wrote down all these theorems that the ancient Greeks knew about numbers, and so Euclid's Elements is like one of the most classical mathematical texts of all time. But Euclid isn't. It's said that Euclid didn't actually prove everything in the Elements. Just kind of wrote down a lot of the stuff that was already out there. But this theorem is attributed to Euclid that there are infinitely number of primes. You guys remember how the proof went? What was the proof technique?
It was contradiction.
Yeah, proof of contradiction. So this is a new proof of Euclid's theorem.
Yeah. Oh,
Everybody get one?
Yeah, there's that.
So this is a journal article by Philip Sadak, and he gave a new proof of Euclid's theorem. So the first half of this journal article is just a one-page journal article, and so he kind of recounts what prime numbers are and the history of prime numbers. This theorem by Euclid in approximately 300 BC, and so the proof goes there are infinitely many primes. Right, so Euclid's proof, and it says slightly modernized. This is essentially the same proof that we proved in class. That assume to the contrary, so assume by contradiction that the set of primes is finite. So then you can list all the primes. So you set, the set of primes P1, P2, up to Pk, and then so it's kind of a interesting trick that Euclid used, that if you multiply all these primes together and then add 1, and then that's the integer that will give you a contradiction. So multiply all the primes together and then add 1, right? And so this provides a contradiction. And so in this article he says that so if you take this integer q, then the GCD, the greatest common divisor of q and any of the p's, the primes, is 1. Right? So why is that true? Sorry?
Primes only have the factors of 1 in themselves.
Right. So, but how come? Well, why couldn't it be pi then? So you're saying so it has to be either 1 or pi for each pi, right? So then you're claiming that it's not. You're saying it's not pi. So you're saying pi does not divide q. So q is not prime, right? So it has. So we've shown that every positive integer greater than 1 has a prime divisor, right? So this has a prime divisor, and we're claiming that it's not any of these primes.
Because if you multiply all the primes together, they won't have any common factors to get q.
Okay.
If you take prime 1 times prime 2, if you multiply all those primes,
Right.
even if you do the prime factorization, it's still all primes.
Right. This is so this isn't. Yeah. This isn't. So this isn't the prime decomposition of q, but.
Well, I know, but what I'm,
Right.
it just won't come out.
So is it clear? Yeah. Is it so you see how these theorems go? I mean, these journal articles. You just write such a small little phrase, and it's like, oh, it's clear, right? It's clear. So it's obvious. It's left to the reader to think about it for an hour. It's obvious to me. So that's what authors do often. I just want to just make sure everybody's clear. Why is the GCD of this number and pi always equal to 1? Another way of saying that is that none of these primes divide q. So you're right. I mean, if it would either have to, for any particular I, the greatest common divisor would either be 1 or this prime. Right? Because the only divisors of pi are 1 and pi. So we're saying that it has to be 1. So think about how could you show that?
If you multiply two p-values together,
Mhm.
you're gonna get an answer that is divisible by those two p-values.
Right.
But then you add one.
But you're
But
adding
then
one.
you add one.
Then you're adding 1, right?
Does it have to do with consecutive integers, like n and n plus one, and now they have no common factors?
Julie said it comes five.
Not being
Well-
consecutive integers.
So yeah, so you're claiming that P1, P2, and PK
All primes are
is
odd.
is one
except for
integer.
two.
The next integer
So that's what it is, two, because you had one to it.
plus 1. So she's saying that these are consecutive integers,
Like n and n plus one.
like n and n plus 1. So you read further down. So
So one's even, one's odd?
the new proof actually uses that fact that if you look at consecutive integers, they're always relatively prime. That's one way you could show it, I guess. So if this is relatively prime to this, then the greatest common divisor of this and this is 1, and so the greatest common divisor, so any of the PIs would also be the commonest factor of this, so they can't be factors of this. So what about, suppose I just rewrote this as Q minus P1, P2, Pk equals 1. You know any other theorems we proved about common divisors?
Linear combinations.
Yeah, so this is a linear combination of these two numbers. And this linear combination is 1. So any common divisor of Q and this would also have to divide 1. But the only divisor of 1 is 1. Positive divisor is 1. So that's another way you show it. Okay, and just think about it, right? Like if something divides this number and something divides this number, you could like factor it out, right? And then it would have to also be a factor of this, and it's the only thing you can do is 1. Okay, so we're kind of unpacking. I'm kind of showing you how you know if you've read a journal article, how much kind of unpacking you would do in just like in 2 sentences. You got to think about the things and kind of really convince yourself when you read a journal article that every statement is true. Okay, so all right, so we believe this now. So the greatest common divisor of Q and each PI is 1. So in other words, PI does not divide Q. Right? So none of the PI divides Q. So that's basically essentially why we get a contradiction. Right? You have a number, a positive integer, and none of the primes divide it. Well, that's a contradiction. We showed that every integer greater than 1 has a prime divisor. So in other words, the proof goes, so there must be another prime that's not in this list that divides that. So that's a contradiction because we just said that all the primes are right here. Okay. So it says, therefore Q has to have a prime factor different from all the existing primes, and this is a contradiction. Okay. So essentially, it's kind of neat that the Greeks were doing all kinds of stuff like this over 2,000 years ago. So this is kind of modernized with the, I guess he says modernized because I don't think Euclid, I don't know if maybe he didn't use the great common divisors notation, I guess. Certainly knew about greatest common divisors, but. Okay, any questions about Euclid's theorem? This is basically the proof we did in class. I wrote out some more details. But basically that's the idea, right? You come up with another, you say there's only a finite number of primes, then you produce an integer that doesn't have any of these as factors. That's a contradiction because every integer greater than 1 has a prime factor. Okay. All right, so let's look at the new proof. So what I'll do now, let me give you guys a few minutes to read where it says new proof. So read that to yourselves, and then we'll discuss the new proof and how it's different from Euclid's proof. If you have any questions while you're reading it, you might jot them down on your paper. Are we ready to discuss the new proof? Okay, we're still looking down, so I'll give you guys another minute or two to kind of digest.
Right, that's why I was.
Where was this cut from?
What do you mean? I don't know, it's just in front of us up here, I'm not sure what it is. Yeah. I mean, you can look it up, I didn't. You like that? Yeah. To me, is that, it's almost funny, like, the way you wrote it, it's kind of, it's hard to believe that this is actually, nobody thought of this earlier.
You kind of want to go duh.
Sorry?
You kind of want to go duh.
Yeah. And there's probably, I would venture to say, probably over 100 proofs of Euclid's theorem. Yeah, at least, I'd say. But, yeah, so the way Euclid proved it is by contradiction. And a lot of, you can prove in other ways. There's a lot of more sophisticated ways of doing it, show it too, like analytic theory, like calculus and stuff. But this is kind of a neat little proof.
He's a associate professor at USC Greensboro.
Okay. All right. So we said that the proof technique for Euclid's proof was proof by contradiction. Is that the same technique that Professor Sadak uses? No. So it's not a proof by contradiction. So in some sense, you might think logically it's actually an easier proof. I mean, because it doesn't use a technique like proof by contradiction. This is actually what we call a constructive proof. So a constructive proof actually demonstrates that there are, actually gives a formula for an integer with an arbitrary number of prime numbers. So it's actually, instead of just saying that something exists, it's actually demonstrating and actually giving you a formula that proves that it exists. So that's called a constructive proof. So it's a totally different flavor than Euclid's proof. So let's look at the first sentence. Okay, so let n be an arbitrary positive integer greater than 1. Okay. So we're saying it's greater than 1. Since n and n plus 1 are consecutive integers, they must be coprime. Clearly. What is coprime? It's the same as relatively prime. Yeah, so that means I usually use the word relatively prime, but maybe I should use coprime because it's easier to write. But coprime means the same as relatively prime. So this is kind of the same issue we talked about earlier, right? If two consecutive integers are always relatively prime, are we convinced that that's true? Is everybody convinced? we'll just look at some examples, right? That's 1 and 2 are relatively prime, 2 and 3 are relatively prime. So it must be true, right?
Even not.
So how did we show that?
Is that
Yeah,
in-
well, they're even and odd, so yeah, well, is that true? So it must be relatively prime.
Then induction proof?
So
Could you do
3 and
Euclid's
6 are
algorithm?
relatively prime, right?
Could you
Because
do
one's even, one's odd.
No, they're not consecutive.
Oh, okay. So
Couldn't you do Euclid's algorithm?
so it's clear. It's clear then, right, everybody? That n and n plus 1 are relatively prime.
Not clear smiling, no.
Clear as mud.
Well, you want to use the Euclidean algorithm? So n plus 1 divided by n. It's 1 times n plus the remainder of 1. Okay, so then n, when I divide it by 1, is 1 times n plus the remainder of 0. So the last non-zero remainder is 1. And so is that, now you believe it? Could you prove it to somebody then? Could you also use that trick, that if I can write a linear combination of these two integers that equals 1, then that would demonstrate it as well, right? Because any number that divides a linear combination of two numbers, any number that divides two numbers would also divide the linear combination. So what should I put right here?
Minus.
Okay, so there's a linear combination of n plus 1 and n that equals 1. So any common divisor of n plus 1 and n would also have to divide 1. Okay, so there's another proof that. So it is true. Every pair of consecutive integers positive integers is relatively prime. Okay, all right. So we've gotten past the second sentence. All right, so they're relatively prime. Hence, the number n2 defined by n times n plus 1 must have at least two different prime factors. Right? Is that clear? Why is that true?
Is that because every integer greater than 1 has prime divisor?
Sure,
And there's
right.
two of them there.
I believe that's right. So n is not greater than 1, so it has a prime divisor. N plus 1 is also greater than 1, so it has a prime divisor. But they can't have the same one because we said they're relatively prime. So there must be a prime divisor of this factor and a different prime divisor of this factor. Is that clear? Okay. So what's the next integer after this number? Oops. N times. Okay, here's one integer. Here's the next integer. So these are consecutive integers. So if I multiply them together, we get another integer, and we kind of repeat the argument, right? So this integer is relatively prime to this integer because they're consecutive integers. So these are relatively prime integers. So we know for sure that this integer and this integer must have at least two different prime factors. But this one has two, this factor right here itself has at least two different prime factors. So there's at least three different say distinct prime factors. Is that clear? So it's just kind of repeating the same argument, right? So these two are relatively prime, so they must have, and since each one has a prime factor, they must be different. This and this are consecutive integers, and therefore relatively prime. So this integer and this integer have two prime factors that are different, but this one has two of itself that are different, and none of those two could be a prime factor of this because they wouldn't be relatively prime. All right, so that has at least 3 distinct prime numbers, prime factors, and we're done. It says this process can be continued indefinitely, so the number of primes must be infinite. So if you continue this process, you could keep building an integer that has as many primes as you want, many distinct prime factors as you want. So that means you could always, like if I said there were only k prime numbers, I could build an integer that has k plus 1 distinct prime factors. So there can't be a finite number of prime factors. Okay? Any questions with that? How about, could you write the formula for N4? Write it down on your paper, see if you, what's the formula for N4? N sub 4. You already did?
It's probably it is what it is.
So, how many parentheses do you need? So you take N3, write it, and then take N3 again and add 1 to it, and multiply this number. So
3 parentheses, 3 and
Yeah.
okay, so there's N3, add 1, and then
I use a bracket.
use bracket. So there would be N4. So the notation. So why did you use this notation for his integers?
It's good to just
better
write it
better
out.
stop right there.
You're guaranteed to have at least this many distinct prime factors. So N4 has at least 4 distinct prime factors, and so on. So that's why I use the notation.
So could you say it continues on forever, and so you get n sub k equals n sub k times n sub k minus 1?
So
Or like, it would be
yeah, n sub
n sub k would equal n sub 2, I guess, or yeah,
minus 1.
n sub k, yeah. Yeah.
so it's a recursive formula. Yeah. You can say that. So what is N1? They didn't say what N1 was.
Would be n.
Is that? Yeah. Okay. Okay. Any questions? There's another proof. So we've proved two different ways that there's infinite number of primes. Actually, we've improved a third proof. Do you remember Dirichlet's theorem on primes in arithmetic progression? We said that if A and B are relatively prime, then look at numbers of this form, where k is an integer. So Dirichlet actually proved that if you look at all the numbers of this form, so like a plus b, a, 2a plus b, 3a plus b, so, and I assume that a and b are relatively prime. Okay, so you take any two relatively prime integers, then you look at all these numbers like this, and he actually proved that this set of numbers has an infinite number of primes. So there's an infinite number of primes of this form, which is kind of neat. So we proved 4n plus 3, is that what we did? Yeah. So we proved that this arithmetic progression has there's an infinite number of primes of this form. So as a corollary, there's an infinite number of primes, right? I mean, because just the primes of this form, there's an infinite number of them. So we have, and this, remember the proof of this was pretty much like Euclid's proof, right? We produced a number, I think it was like, take all the numbers of that form and you multiply them together. You assume there's a finite number of them, multiply by 4, and then add 3, and then this we get the same kind of contradiction. So it's essentially Euclid's proof that there are an infinite number of primes of that form. Okay. Any questions about this? So let's prove another proof that there's an infinite number of primes. It's going to be kind of like this arithmetic progression right here. So there's actually a theorem. The arithmetic regression. Well, let's just put it this way. There are infinitely many primes of the form 6k plus 5. Okay, so the proof is going to be very similar to the proof we did here. It's it's a proof by contradiction. You assume there's only a finite number of them, and then we're going to build an integer that will give us a contradiction, something like this. The way you put it. You guys are going to help me. Okay, so to the contrary, suppose only a finite number of such primes exist. Okay, call them P1, I said P0, P1, P2, all the way up to PK. Okay? So suppose, just like we did with Euclid's proof, suppose there's only a finite number of them. We can call them P0 through PK. Here is the integer that's going to give us the contradiction. So form the integer n, which is 6 times all these primes, P0, P1, P2, up to PK, minus 1. It's minus 1 this time. Why the minus 1? Because that's what works.
Okay, so here's my question. How am I supposed to know that if I'm doing this myself?
Trial and error. Yeah, I mean, that's the way proofs are. You try something. You might have tried. You wanted to try plus 5?
I'll go with yours.
But you wanted to do plus 5, right? Well, this is congruent to 5 mod 6. So that's actually one of the things we're going to use. This actually is, it is equal to an integer of this form. It is, so that's one thing we're going to talk about. So this is 1 less than a multiple of 6. So you could also write this as 5 more than a multiple of 6. It's just that this is nicer. This will help us out. Okay. That's a good question. So, all right. So I have a bunch of claims, and this is kind of the way, if I was just writing this as a polished proof, I would leave out all the details and just say, well, clearly this is blah, 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 and therefore it's true. Right? So I want you guys to help me out with all these claims. So the first thing is kind of what I just mentioned. Claim 1. This capital N is of the form 6k plus 5. You believe that? Do you know what I mean when I say other form 6k plus 5? It means you can write it as 6 times an integer plus 5. Okay? Does everybody believe that?
No, it doesn't help.
I thought it was 6K minus 1.
It is. But it's also 6k plus 5. I mean, it's of the form 6k plus 5. Prove it with congruences? Yeah, so n is congruent to -1 mod 6, right? It's one less than a multiple of 6, but that's the same as saying it's 5 mod 6. So that's the same as what I claimed, that n is 5 more than a multiple of 6. -1 is the same as 5 mod 6. If it really bothers you, I mean, you just factor out one factor of 6 from this group, factor out a factor of 6, and then you have or take away a 6, and then 6 minus 1 is 5. I mean, so that's essentially what we're claiming. Okay? Everybody believes claim 1. All right. So n is in the form 6k plus 5. Claim 2. This one should be easier to believe. N is bigger than each of these primes, pi. You buy that? Or buy that? How much? Buy for? Already paid your tuition. All right, so you mind tapping that? No, if it's, I gotta log in again. Okay, so everybody believes n is bigger than each pi?
Yes.
We'll see it recording. Well, the screensaver's on. I don't know. So all right, so claim n is of the form 6k plus 5, and claim 2, n is bigger than each of the pi. Everybody believes that? Okay, good. All right, claim 3. So these are all the things that we're going to need to prove this statement. So no pi divides capital N. Everybody believes that?
That's why the minus 1 is more useful than the plus 5. Correct?
Yeah, that's one of the reasons. Yeah, so none of the pi's divides n.
Because that guarantees they're consecutive. Yeah.
Mm-hmm. All right, so is that clear? This is kind of the same argument we've seen a few times today already, right? Like if a pi divides this n, then it would divide their difference, and then it would divide -1. But it's impossible. There's no primes that divide -1. Okay. So none of the pi's divide n. Claim 4. So this is not the typical way you write a proof. I'm trying to show you all the different things you have to think about before I would just like write a conclusion. 2 and 3 do not divide n. You believe that? So why does 2 not divide n?
It's a divisor of 6.
And then just subtract 1.
So this is even, and subtract 1. This must be odd, right? So 2 doesn't divide it, but 3 does not divide it. Why?
Because it's one number less than the power of 6. Or
Yeah, it's we said it was 5 mod 6, and so it would be 2 mod 3. So it definitely does not divide 3. In other words, if 3 definitely divides this part. So if 3 divided the whole number, then 3 would also divide -1. Again, it can't. So no prime of the form pi, and 2 and 3 also do not divide capital N. Okay? All right, we good so far? All right. Claim 5. Do you remember the lemma we needed to prove this had infinitely number of primes? It was one of your homework problems. Is that one that's due tomorrow? So you guys all prove that any integer of the form 4n plus 1 times another integer of the form 4n plus 1 is also 4n plus 1? That's one of your homework problems? Okay, yeah, so we needed that theorem here, right? Or that lemma. I left it as an exercise. So we have a similar claim here. Claim 5. Every prime greater than 3, prime p greater than 3. Well, I need this claim first. Is of the form 6k plus 1 or 6k plus 5. And then the next claim is going to be that if I have primes of the form 6k plus 1, when I multiply them together, I'll still have an integer that's of the form 6k plus 1. So that'll be our next part. All right. So do you believe that every prime greater than 3 is 1 more than a multiple of 6 or 5 more than a multiple of 6? You believe that? How could we show that?
Same thing with the mods, couldn't you? Because if it's 1 less than multiple of 6, that would imply it's 5 more than the previous multiple of 6.
Okay. So there's only think of this as like maybe like residues or mod 6. So and I'm basically saying every prime greater than 3 is 1 mod 6 or 5 mod 6. Can a prime number be 0 mod 6? Why? No, it can't. Why not? It wouldn't be prime. That means it's divisible by 6. Can it be 2 mod 6? Can a prime greater than 3 be 2 more than a multiple of 6? No, it would be even. Okay. So by the same reason, it can't be 4 mod 6. Right? It can't be 4 mod 6 either because it'd be even. Can it be 3 mod 6? Then it'd be divisible by 3. So the only possibilities left over are 1 mod 6 and 5 mod 6. So if P is 0 mod 6, let's just fight. If P is congruent to 0 mod 6, then, well, it's even, so 2 divides P. If P is congruent to 2 mod 6, then P is even as well. If P is congruent to 3 mod 6, then it's divisible by 3. If P is 4 mod 6, then P is even again, so then 2 divides P. So that takes care of all those 4 cases. So the only cases left over are 1 mod 6 or 5 mod 6. So P must be 1 or 5 mod 6. Right? So that's essentially what I said, right? So any prime greater than 3 is congruent to 1 or 5 mod 6. Okay? Times 6. 6. If m and n are of the form 6k plus 1, then so is m times n. You believe that? How did you prove it for 4k plus 1?
Well,
See, I don't approve this. This is like you use the same proof in your homework. So you could use a definition. I mean, you could use a definition. You know, you could write M as 6K. Let's say 6K plus 1, and write N as 6J plus 1, whatever. If you multiply them together, you'll see you end up with an integer that looks like 6 times an integer plus 1. Okay. So I'm not going to write the details out because it's their homework, basically. But everybody believes that. So if you multiply, you kind of reason it out. All right. So, all right, we're ready for put this all together. Everybody believes everything, all these claims, right? All right, put this together. So since n is of the form 6k plus 1, 6k plus 5, and n is bigger than each pi. Okay, we already established those claim 1 and 2. N must be composite. Why?
So we said there was a finite number, so if it's bigger, then it would not be in that list.
Good. So n is not, n can't be one of these guys in this list. Right? Because what's bigger than every one of them, so it can't be in that list. And if if it was prime and bigger and still of this form, it would have to be in that list. So, okay. So basically, it has to be composite because n is not in that list of primes of this form. Okay. So the idea is, otherwise, our list would not be exhaustive. It wouldn't have every prime of this form. Okay, but 2 does not divide n, 3 does not divide n, and no pi divides n. But 2, 3, and no pi divides n, right? So we just said that all the other primes are either of this form or this form. But none of the primes of this form divide n. 2 and 3 don't divide n. So every prime dividing n must be of this form. By that? Right? So 2 and 3 and none of these guys, none of the primes that are 6k plus 5 divide n. So n must be the product of only primes of the form 6k plus 1. Okay? See why? None of the primes dividing it are of the form 6k plus 5. 2 and 3 don't divide n. So the only primes that are possible to be divisors are of the form 6k plus 1. But why is that a contradiction? By claim 6, it's impossible. Because if you multiply a bunch of primes of the form 6k plus 1, then what does the product look like? The product would also be of the form 6k plus 1. That's a contradiction because we already assumed that we already figured out that n is of the form 6k plus 5. So this is impossible. Because a number, let's say, for the product of numbers of the form 6k plus 1 is also 6k plus 1 and n is of the form 6k plus 5.
Dr. Seven, can you go over once again why n must be the product of primes in the form 6k plus 1?
Sure. Okay. So it has to have a prime divisor, right? Has to have a prime divisor. Okay, because it's composite. Right? It's composite, it has prime divisors. But we showed that every prime greater than 3 is of these two types. We ruled out anything that's of this type. They're all the PIs. So none of these guys are factors. 2 and 3, the number of the primes that are less than 3, don't divide n. So the only possible candidates for primes dividing n must be of this form. Okay. So we used claim 1 and 2 to prove it's composite. We used claims 3, 4, and 5 to prove this statement that n must be a product of only primes of the form 6k plus 1. We used claim 6 to show that n must be of the form 6k plus 1, but that's a contradiction because n is of the form 6k plus 5. So that's how we get a contradiction. Therefore, our original assumption was false. We assumed that there were only a finite number, and so that must be false. And that is a pathetic square. There we go. Any questions? So Euclid probably could have proved this, right? I mean, he used essentially the same technique to prove that there's an infinite number of primes. So as a corollary, there must be an infinite number of primes, right? Because there's an infinite number of primes just of this form. Okay. All right. So that's all I want to do today. I did want to talk about the schedule for the rest of the summer. You know, our meeting dates. We're meeting next Tuesday, right? 17th, again from 9 to 11 a.m. And did Dr. Whitaker mention your class this afternoon is in the library in the basement? So that's the classroom that we typically use. Like I used last semester to record my lectures. So I think from now on we'll probably meet over there. It'll be a lot easier. All the cameras, everything's already set up. So that'll save me from trying to use all this stuff that's not working. So we'll meet over there. That's I think it's Library 108.
That's what he said.
Yeah. Then July 1st, exam day. So you have an exam in Dr. Whitaker's class the same day, right? I mean, it's kind of the way it is, right? Like we only have 5 classes, and this is like the halfway point. So that's really the only possible day we can have a midterm type exam. So, but we'll have an in-class exam.
Will that also be in the library?
I guess. Well, actually, there's much more room in here than there is in that room. So we'll probably stay over here for that one. So what room is this?
109.
Massey 109.
Can you get us like a study guide for that, or is it?
It's going to be, yeah, very, very much like homework and stuff you've done for homework. I mean, it's kind of what my philosophy